Hi, welcome to this organic chemistry quick video. This is Aromatics Part 3, Aromatic Nucleophilic Substitutions. As you've heard a few times by now, there are 3 flavors. This one is all about the nucleophilic substitutions. Same type of an introduction that we had before. Benzene is stable, doesn't usually react, but we've got another exception. The last exception was when we had an electrophile replacing an aromatic hydrogen. This time we have a nucleophile replacing an aromatic hydrogen. So we call it aromatic nucleophilic substitution, or, whoop, that should be ANS. My bad. Okay, there are 3 main requirements for us to do this in the traditional way. First of all, benzene must have a strong electron withdrawing group attached, or you have to be at very, very high temperatures and a weaker electron withdrawing group. You still need withdrawing groups. Benzene also has to have a good leaving group. And remember, a good leaving group is the conjugate of a strong acid. And the leaving group must be ortho or para. So ortho is directly across, para is right next to the electron withdrawing group. You can't have meta. And here's the reaction mechanism. The very first step, you've got your nucleophile, which here we're showing as a negative OH, so a hydroxide, is going to be attracted to the most positive carbon on the benzene ring. The carbon where your leaving group, in this case chlorine, is attached, not only has that chlorine sucking electrons away from it, making it positive, but on the opposite side of the molecule, it's also got that strong electron withdrawing group of NO2 sucking electrons away. So that's a nice positive carbon. OH will attack. And that looks a lot like an addition, right? Because we're attacking across a double bond. And then you go through this, what's called the Meisenheimer complex. Meisenheimer because it's the middle complex where your electrons chase each other all the way around the ring. And then you're going to have the loss of a leaving group, which when you have a leaving group and you form a double bond, we call that an elimination. So this type of reaction is called an addition elimination. And I'll show you a video of that here at the end. If you don't have a strong electron withdrawing group, there is another way to do this reaction, and that is elimination addition. So last one was addition elimination, this one's elimination addition. For this, you have to have a really crazy, wicked, strong base. And our favorite wicked, strong base that we have, which is what we use to make our alkynes, is sodium amide. I said that we have NaNH2. Usually it's in ammonia, and you need a strong acid in the end in order to reprotonate whatever you're adding. Okay? So leaving group and or a beta hydrogen are replaced with your nucleophile. And you might be asking why? Well, here is the actual reason. If you look at this reaction, first step, we're going to have the deprotonation of our most acidic hydrogen. Most acidic hydrogen is going to be directly next to our leaving group, which is pulling on those electrons. So you pluck off that hydrogen, and then you're going to end up forming a triple bond. So the lone pair kicks over and kicks off your leaving group, and then you have what's called a benzyne. Okay, benzene, except it's got a triple bond in it, and that looks super weird, and it is super weird. Then your nucleophile can attack. You'll have your lone pair move back over onto either the location where your proton was removed or the location where your leaving group left, because both of those have equal opportunity. And then last step is your, it's called your acid workup step, and that's where you add your hydrogen back onto the benzene ring. This is the memory book page for it. So the first one is elimination addition. Your leaving group has to be ortho or para to your withdrawing group. And then the elimination addition, this part might not make a whole lot of sense, but if you pay attention to the way that the benzene ring is oriented, it kind of tells you that you're either going to replace where your leaving group was or adjacent. Now the difference between the top one and the bottom one is the top one is with a high temperature, and that high temperature can actually cause your gamma hydrogen to be removed occasionally or replaced, which is a little bit more rare. Usually it is where it will replace your leaving group or it will replace the location next to it. And then if you're using the really strong base, it'll only be in those 2 places. So now we're ready to go look at those videos. And the first one that I've got pulled up, this is the addition elimination. So it's got the crazy strong leaving group. Going to go ahead and hit play. So nucleophile comes in and it's attracted to that positive carbon. Electrons chase all the way around the ring until they get back up to the top, and they kick off your leaving group. Goodbye, leaving group. And that's it. Okay, we'll watch it a second time. Nucleophile comes in. Electrons move all the way around the benzene ring until eventually they get back up to the top, and that leaving group's like, I'm better off without you. Okay, so that was the the addition elimination. Now let's look at the elimination addition. So our strong base comes in and deprotonates. You've now got that, you're going to form the triple bond, and then your nucleophile comes in, attaches, and you do your acid workup, add your hydrogen. Watch one more time. Base comes in, deprotonates, formation of your triple bond, leaving group leaves, and then your nucleophile comes in and attaches. Negative charge is attracting to your acid workup step, and that's it. I hope that this helps, and I'll see you guys later. Bye.